In this lesson, we're going to investigate exponential functions and see how they behave. We've worked with quadratic functions like y equals x squared, where we got a variable to a second power. But what happens when we flip that around and we put the variable x in the exponent? Well, this becomes an exponential function. So a simple exponential function is of this form: f of x equals a times b to the x, and the key is that the x, the variable, is in the exponent. So b has to be positive, that's important, and it can't be 1. If it's 1, that doesn't make any sense. And the number a is what we call the initial value, and the number b is called the base, just like regular exponents. So we got some base to some power. That's a variable. So, with that in mind, which one of these are exponential functions? Well, we have 2.5 to the x. Is that exponential? Yes, it is exponential because there's a base that's not 1, and it's positive, and we've got a variable in the exponent. What about negative 3 to the exponent? Negative 3 to the x power, sorry. No, that's not, because we have a negative base. All right, we've got to have a positive base. What happens here is if you have negative 3 to some power, now remember, x can be anything. So if this, what happens when x is like 0.5? Well, that's negative 3 to 0.5. Well, what does that mean? Well, negative 3 to the 0.5 means the half power, and a half power, we've learned, means a square root. So this means the square root of negative 3, and the square root of negative 3 is not a real number. So that doesn't work for us. So x cannot be, the base, that is, cannot be a negative number. All right? Well, what about this one here? What about 2 to the negative x? Is that exponential? Well, it sure looks like it's in this form, but there's a little negative up here. There's a positive x. Well, there's a little, we got to work a little magic here. This is really the same as 2 to the negative 1 to the x, right? Because we know that a power to a power, we multiply. So negative 1 times x is negative x. So yes, these two are the same thing. Well, what is 2 to the negative 1 power? Well, a negative exponent is going to make it into a fraction. I'm going to drop that 2 down to the denominator. And we end up with this. So this is just 1/2 to the x power, and that's fine. B, the base, has to be positive. This is our base. The base is positive, and it's not 1. So this is great. This will be 1/2 to the x power, and there's no problem with that. So yes, this is exponential. Well, what about this? 2 times x to the third. Well, it looks pretty good. Let's compare it to our generic form here, our general form. No, the problem is x is in the exponent. Here it's not. This is just a cubic function. So the x isn't in the exponent. All right, so an exponential function has to have x in the exponent. That's the key. All right, so now that we kind of have an idea what an exponential function is, let's look at a situation that will give us good understanding, at least a good respect for exponential functions here. So this is the legend of the inventor of chess. So the legend has it that there was a peasant in India that invented the game of chess, and the ruler of the land was so pleased with the game that he wanted to reward the inventor for his creation. So he invited him over and said, hey, you know what, I'll give you a reward. I want to reward you for your popular new game here. And the peasant said, you know what, I don't need much, but here's what we're going to say. I'm going to say, why don't you take my chessboard? It's an 8x8 board. It's got 64 squares on it. And so here's what the peasant asked for. He said, let's put 1 grain of rice on the first square. Then let's put 2 grains of rice on the second square. And then let's go ahead and double that. And we'll put 4 grains of rice. 1, 2, 3, 4 on the next one. And then we'll put 8. 3, 4, 5, 6, 7, 8. And we'll keep doubling and doubling. All right, then we'll have 16. Then we'll have 32, 64, so on and so forth. So we'll just double the grains of rice for each square. All right, that's not that big a deal, right? And then I'll have some rice and be able to feed my family, and that's all good. So, the king said, "Oh, that's not too bad. All right, let's give this guy his grains of rice. All right, so let's figure out how much rice this peasant will get. All right, so let's start by writing an exponential function for the grains of rice g on a given square, and we're going to start the first square at square 0. It works a little easier this way. All right, you'll see why. So let's make a little table real quickly. All right, square and rice on that square. All right, so square 0 had 1 grain of rice. Square 1 had 2 grains of rice. Square 2 had 4 grains of rice. The third square got 8 grains of rice. The fourth square 16. The fifth square 32. The sixth 64. So on and so forth. The seventh 128. Now remember, we started at 0, so that would actually be the edge of the board. So it's really 8 squares, but we'll call it square number 7. You'll see why. Well, what's going on here? Well, from here to here, we're doubling, right? So this is really just that 1 times 2. And then from here to here, we're doubling again, right? We're taking that 2 and we're doubling it. So we're taking what we had before, 1 times 2, and we're doubling that. And then we're taking what we had there and we're doubling it. So we have 1 times 2 times 2 times 2. Now, because we have the 1 times 2 times 2, and we're doubling that. See that? Well, that's a lot of 2's. What's a better way to write that? Well, this is really just, we can just 2 times 2 is 2 to the second power. And 2 times 2 times 2 here is just 2 to the third power. And if we wanted, we could write this guy here as 2 to the first power. You see a pattern there? This is 1 times 2 to the first, 1 times 2 to the second, 1 times 2 to the third. Oh, we have 1 times 2 to the fourth. And 2 to the fourth is 16. And 1 times 2 to the fifth, and 1 times 2 to the sixth. All right. There we have it. All right. Now, if we, so we have a function here, all right? So letting the first square be 0, that is. And so the grains of rice, g, is, let's write it as a function, g of n is going to be 1 times 2 to the n. And we actually don't necessarily need the 1 there. That 1 is our starting value. That's what we had on the 0 square. All right. So now the question is, how many were on the last square? Well, there's 64 squares, so the last square, since we started at 0, the last square is going to be n equals 63. So that would be g of 63, which would be 1 times 2 to the 63rd. All right, and we can go calculate that. So let's get our calculator going. We've got 1. We don't need the 1. We got 2 to the 63rd power. All right, that's the grains of rice. All right, this is scientific notation. This is 9.22 times 10 to the 18th. All right, approximately 9.22 times 10 to the 18th, which means we're going to move this decimal point 18 times, and we'd have 922 and a whole a lot of decimal values. Now that's an approximation, okay? I think I need 3 more here. All right, now I round it off. So that's approximately that many grains of rice. All right. And so, needless to say, they ran out of rice pretty quickly as they were filling up his board. And I don't know, I think the end of the legend says something like they never heard from the peasant again because the king could not fulfill his agreement there. So, anyways, legends aside, let's see. Now, let's compare that to the world's production just to see how much rice that is. The world makes 5,000 million metric tons per year. All right, a metric ton is 1,000 kilograms, and a grain of rice is about a 64th of a gram. All right, so let's see real quickly here. Let's go back to our number here. All right, and let's just get this. All right, so that's how many grains of rice. Let's divide that by 64. Let's take our answer divided by 64. Okay, there's how many grams. Now let's divide that by 1,000. Take that answer and let's divide that by 1,000 because there's 1,000 kilograms in 1,000 grams in a kilogram. So that's how many kilograms we have. There's 1,000 kilograms in a metric ton. All right. So if we take that number and we divide it by 1,000. Okay. So there we have that many metric tons. All right. So if the king were to fulfill his agreement, again, he'd have this many grains of rice divided by 64. This is in grams. Divided by 1,000, we have kilograms. And so then kilograms divided by 1,000, we have metric tons. A metric ton is 1,000 kilograms. All right. And the world production right now is about 500 kilograms. I'm sorry, 500 metric tons per year. So this is how many years it would take. It would take over 288 million years at our current production. All right. So if the king were to fulfill that, it would take 288 million years. Now, by the way, that is just to fill the last square. All right, that's for the last square. All right, it turns out that the whole, if you were to add them all up, it would be double that. All right, so if the question how many liters, okay, or how many metric tons. Let's change that to tons because that's what we were working with there. How many metric tons would it take to fill the whole board? Well, it would take, let's just say it would be twice as much. Okay, 2 times as much. All right, so it would take twice as long to fill the whole board. All right, that's how powers of 2 works. All right, well, pretty amazing and almost unbelievable, but that's the power of exponential functions. So now that we have an appreciation for exponential functions a little bit there, let's look at some more examples. That's an exponential growth that we just saw. Another situation that happens is what we call exponential decay. And this happens with medicine a lot and chemistry. So suppose we have a patient that is given a dosage of 320 milligrams of penicillin. All right, and it's given intravenously, so right away it's in the bloodstream. All right, so we'll assume that half the drug is absorbed by the body each hour. All right, so the question is to find the amount of penicillin in the patient's bloodstream each hours after the the drug is administered. Okay, so let's look for a pattern. Okay, all right, so we had 320 milligrams to start. After 1 hour, we had half as much, 160. After 2 hours, we had half as much, 80 milligrams. After 3 hours, we had half as much. And after 4 hours, half of that, 20. And in 5 hours, half of that, 10. All right, so what's going on? Well, we're dividing this by a half. So to go from 0 to 1, we've got 320 times a half. And then we're going to multiply by a half again. So we got that number, which is half of 320. Come on. And we're going to multiply that times a half again. If we take 320, we half it, and we half it, we get 80. Okay. If you take 320 and we half it 3 times, then we get 320 times a half times a half times a half is 40. Now what's a quicker way to write that? That's 1/2 to the 3rd power. And this is 320. This will be times a half 4 times. So a half to the 4th power. And this is 320 times a half to the 5th power. All right? And we can rewrite this one here. We'll write this. This is really a half times a half, which is a half to the 2nd power. And a half to the 1st power. We see a pattern? Okay. So, we can write an equation for this. The amount of penicillin after T hours would be 320 times 1/2 to the T power. This is our starting amount, you'll notice. And 1/2 is this ratio that's happening every hour, 1/2 as much. If it was 1/3 as much, if we were cutting down by 1/3, if it was getting absorbed faster, this would be a 1/3 to the T power, okay? So we can now use our equation to predict how much penicillin will be in the bloodstream after 10 hours. Maybe 1/2 to the 10. And we can use our calculator there. And using our calculator, we can see that 320 times 1/2 to the 10th power. Make sure you use parentheses there, by the way. Would give us 0.3125. And that is, what was that? Milligrams. Okay. Now, here's an interesting question. Will the penicillin ever be completely out of the bloodstream? It actually won't. Because every time we half, there's something left. All right, and so when we have exponential decay, there's always something left. Now, it might not be measurable. It might be what we call negligible, but there will always be something left. All right, that's an important property of exponential decay. So this is what we call exponential decay. So an exponential function written as a times b to the x is either exponential growth if that b value is bigger than 1. So if this is bigger than 1, it's going to be growing. Okay, if it's 2, 3, 4, 5, or even if it's 1.1, it's going to be growing, growing, growing. Just it's maybe slowly if it's like 1.1, or a little quicker if it's like 2 to the x. If this b value is between 0 and 1, we call this exponential decay, and this is the decay factor. Okay, so the penicillin decay factor is 1/2, and the rice growth factor was 2. All right, so that's how exponential functions work. And next we'll be looking into graphing some exponential functions to understand them better.